All right, thank you very much for the introduction. It's a pleasure to be here, also a great honor to participate in this event. Let me start with a few maybe comments on my background. So I was trained as an electrical engineer and then increasingly moved towards computational and applied mathematics. And as part of this move, I also got in contact and worked together with the UK Met Office for a few years and then with the German Met Office. And that got me into the field of data simulation, where I actually met Miyoshi a few years ago, or several years ago now, not a few, actually quite some years ago. And that got me into data simulation. More recently, I also got very interested, and actually independently of this particular Moonshot 8 project, on control theory. So I'm now investigating, or I'm generally interested in how to combine data simulation and control, which of course is at the very core of this project. But it actually goes beyond this project, because it's actually part of what has now become very prominent in applied sciences, the concept of a digital twin. And digital twins are now being used in engineering, designing aircrafts. It's used in personalized medicine, in the geosciences. Well, it's still not showing, so I will keep talking a little bit. And so it's very exciting to see this here, but also it's actually affecting, I think, I looked at the different Moonshot programs. It's Moonshot 1 will also benefit from these concepts of a digital twin, where you build a computational mirror of a physical process with a dual interaction, where you take the data from the physical object and then adjust your computational models. And the computational models then inform control or decision-making by humans on the... Oh, here we go. Now we can move on. Okay, thank you very much. Okay, and in fact, this idea can be traced back to John von Neumann, who famously stated in the 50s already that, you know, in fact, in the context of meteorology, that was one of his big interests in there, and the newly developed computers, electronic computers. You know, he said, all processes that are stable we shall predict, all processes that are unstable we shall control. It's exactly what Miyoshi just pointed to, right? So the idea, I mean, was basically put forward, but of course in the 50s, John von Neumann, there wasn't the mathematical tools or computational tools available, but the insight was very foreseeable. And so then in the 60s, the field moved forward in a big step. And it got to the understanding that actually two concepts of control, this sort of control that where you actually apply some additional terms to the system, to the process, and you change the behavior of this system. That's control theory, which goes back to Bellman in the US and then Pontryagin in the Soviet Union. At the same time, it was understood that you can use data which you observe to adjust mathematical models so they stay aligned with the physical process. And that's also a kind of control. In fact, there is a duality. And Kalman was one of the people who developed the theory in the linear context. And again, Stratonovich on the Soviet Union side. And the exciting thing now is in meteorology, we're now moving towards realizing this vision of John von Neumann, essentially. And he actually wrote famously, or he stated famously, it was a talk he gave, that if we can do this, the problem with meteorology will be solved. That's it. So if you solve Moonshot 8, then you solve the problem of meteorology, right? So that's a grand vision, but it's a long way to go there. And it's a difficult and challenging way. So let me start with just highlighting again the two concepts of control theory before we move into the difficult part. So let's start very simple. So let's assume you have a linear system, linear ODE, with a decaying motion that goes to 0. Now the control task could be you want to go somewhere else. You don't want to go to 0. You want to go to 1. And then you introduce a control, U, which depends on the state of your mathematical model. And let's say assume it's linear. So you have two parameters, alpha and beta. And then you have to decide on alpha and beta. So you need a cost function. You need something, you say, what do you want to optimize in the goal to reach point 1, let's say. And then you solve this control problem, the optimization problem, and then you can add the control to the system, and you have a control system. Now you say, okay, I'm done now. No, you're not, because that's a mathematical model. It's not the reality. You have to, if you want to apply this control, you have to understand the state of the physics, of the physical model, or not the physical, I mean the physical process. And so in order to apply the control, you have to know where you are in the real world, or what the weather is at the moment. So that's where data assimilation comes in, where you then say, well, I can collect data. And I assume here is continuously, you can continuously observe, like some satellite data, so you can continuously observe, and you can connect the observations with your mathematical model, and then you again add a term to your mathematical model that ensures that the mathematical computational model stays close to the physical process. And that's this here, right? So sorry, this it's a bit, it's a high, so this here, this term here, right? It's like a nudging. But if you look at the two equations, they're very, very similar. I mean, there's a parameters that are unknown, and there's an added term, and that is actually a manifestation of a deep mathematical insight into this problem, so that there's this duality. And so, for example, a lot of technology that has been developed in metrology, in particular on data assimilation side, can be used in control. And control for a long time has been informed by insight. Data assimilation has been informed from insight from control theory. Okay, so this is a very cartoonish thing, but it's clear, I think, hopefully, that you need both. I mean, you need to combine now both if you want to control the weather. You need an estimator, and then you need a control term. And that there's synergy to be explored. Now, the concept of a digital twin is basically saying, is formalizing this and saying there's a physical process that's called a physical twin, which you can observe, you can take measurements of. Then you have a digital twin, which is a computer model, which of course is a huge simplification of the real process. But it allows you to make predictions in real time. Everything is real time now. And the predictions are then compared with the measurements, and that leads to the adjustment process, which is data assimilation. The difference is called innovation, and then the innovation is inputted to the digital twin to make sure the physical process and the digital twin stay close. And that works extremely well in meteorology, or quite well in meteorology, as we experience. And we also know that's not perfect, right? So sometimes an extreme event is missed, or the precipitation is not correctly predicted. It's extremely difficult, it's very chaotic. But the new thing now is that the digital twin is not only mirroring like we do in weather forecasting, it's now, there's a term actively going back to the physical process. And that's the control. But it can also be decision making. I mean, decision making also a sort of control. So there can be a human in the loop as well, and will be in general, right? You will make decisions whether to interfere with the weather. There will be a human in the loop. But anyway, so now the whole thing is really interacting in a rather complex way. And the really challenge is to make that absolutely safe, and so that you don't trigger extreme events by this. Now, mathematically speaking, this is partial observed market decision processes. Again, it goes back to the 70s, but it's still essentially an open problem in many ways. How to do this? It's so challenging. I will, in the next few slides, I will try to indicate to you why it is so extremely challenging. But it requires, if you really want to make progress, it requires one thing, of course, you have to understand the physical processes and how you can actually control this. This is not my subject. My subject is to say, if somebody can tell me, you know, this is the way we want to control it, can we build a digital twin for this process that safely then derives control laws that are applicable, right? But there is another layer to it, the physics, right? I mean, understanding the physics, right? And what can you actually control? How can you influence the weather? And the field experiments, I suppose, contribute to this subject. But on the digital twin side, it's, the model has to be very fast, so it's model reduction. Now, of course, these days there is generative modeling, foundational models, data-driven modeling is coming to the forefront with the promise to maybe run much faster and maybe to higher accuracy even such models. And then you have to combine this with data assimilation and optimal control. But the key thing is, I believe, that you have to provide a quantification of uncertainties on all levels, because that will help you to mitigate risks, right? Because if you just have like one forecast and you don't see the spread of all possibilities properly represented, then you run into danger, in particular if you're then trying to control the events. So I think this is one of the key challenges of this program, to guarantee such reliable and robust quantification of uncertainty that mitigates risks. Of course, everything has to be done online as well, so that's another severe challenge. Okay, so this aligns, I think, perfectly. I checked on the web page, I looked at the original, let's say, sketch of the program, and you see it says construct control theory, improve predictions, accuracy of predictions, so that's all on the digital twin side. It just aligns perfectly with what I said. And then, of course, on the physics side, it's, you have to develop the technologies on how to influence and how to apply controls actually to real weather. Again, that's a subject I'm not talking about and I'm not qualified to talk about. So let me just scare you a little bit. I mean, if you're not a mathematician, right? So these are pretty dense formulas. So the physical process is a continuous time, space-time process. It can be described by the Navier-Stokes equation. So in principle, there is a physics, multi-physics processes, etc. So in principle, there is everything we need to know, but we cannot possibly put this on the computer, right? It would take too long. The resolution is simply not there, even with today's supercomputers. So a digital twin is always a severe simplification of the truth, the true processes. And then typically it's a finite dimensional computational model you can implement. And so there is a term which will be in green in the rest of the talk, that you have to then try to mimic that in your model. That's part of this uncertainty quantification. You have to quantify the model errors to some degree. And the other thing you have to do is to, of course, connect the digital twin or the computational model with what you're actually observing. And that's called the forward model. So Y is an observation you can take, typically very sparse observations, even though, we have lots of data in the meteorological context, but still sparse compared to complexity of the whole process. And that sort of, this thing connects the digital twin with the physical twin. And then comes, so this is a classical data assimilation context. And then working in this context. Now, if you want to do control, then suddenly there's this U here. And of course, the G, as I said, that has to be given by the physicist, the meteorologist, and understanding what can you do, right? The G has to be derived from insight of how you control. And the cost function, if you really want to do it properly, you have and take all uncertainties properly into account, you have to do a lot of averaging. You have to average over the uncertainty in the initial conditions, right? Because you don't know exactly where the weather is currently. You have to take into account the modeling errors, these here, these uncertainties. So it's not, it's not deterministic completely, even though most meteorological models work deterministically. And then there's the question, what are you going to observe in the future? Also, that has to be basically taken into account. What are possible scenarios that can arise in the future? So there are all these expectations essentially involved, and which would need to be taken care of. What is done currently? Well, you ignore most, just because of otherwise you cannot progress. So for example, you assume exactly you know where you are. So you take your best estimator, and that's your starting point. you ignore the impact of future observations because you don't have them. But you basically, I mean, as a statistician, you actually have a statistics of future observations. I mean, it's not a complete black box. It's just that you haven't seen the specific realization. Anyway, all these things are ignored, and often even the model errors are dropped. You use a fully deterministic system. And that's, I think that's, as I said, I think that you have to be very careful what kind of uncertainties you can ignore and which ones you should acknowledge and make part of your decision process. Again, to mitigate risk of missing something that could harm you in the future. So most current sort of approaches, data assimilation and optimal control, basically treat the thing separately. As I had on the very early slide where I had this one column saying you do the control, compute the control, and then you have the estimation, and then you stuck the two together sequentially. That's very natural, but it's suboptimal, and that's still okay maybe. Suboptimality, we know this from machine learning. Suboptimality can sometimes help you actually. But it's definitely an inaccurate quantification of uncertainties. That's, I think, where the critical thing is. So, and yesterday we had a symposium which I was lucky to be part of on the Moonshot on the mathematical progress of the project. And I saw already a lot of work in progress in this program here in really connecting all three parts. The predictive model, the data assimilation, and the optimal control parts in a unified framework. I think there's still a lot to work on, and there's a lot of potential, but I've been very impressed by what I saw, and I was very happy because it aligns with my own perspective, and actually a lot of scientists in the field. And, anyway, so of course, how can we make further progress? So we already have a lot of very powerful tools. Ensemble prediction was introduced by now a long time ago. And it was actually introduced because we had the computer power suddenly. So it was driven by technology and then computational implementations. Then with ensemble prediction, ensemble command filter came along. And the program director, Miyoshi, is one of the pioneers in this field of ensemble data assimilation. So if you have questions, then please ask him and not me. So he implemented the system in Maryland and also in Japan then. So that's on the meteorology side. But then there's also been progress on the control side in reinforcement learning, in machine learning, model-free approaches. It's instrumental for autonomous driving. But in fact, in reinforcement learning, you're also ignoring a lot of uncertainties at the moment. And then there's the class of model predictive control, which has been pioneered by engineers, chemical engineers. And it's the second class of a big class of approaches to control. And so what are the new, for my personal, it's a bit of a personal flavor, what are the new kids or the new chances on the block? So, so there's also for machine learning and also in data assimilation, we've seen a lot of, it's all probabilities, right? Uncertainties are described by probabilities. And so you have to match probabilities, you have to couple probabilities. And we have a much better understanding now how to do this computationally, to go from one distribution to another, like in Bayesian inference, it's the prior and the posterior. And, but also under dynamics and how to do generative models, it's all relying on basically coupling of transport or coupling and transport of measures, mathematically speaking. It's extremely fascinating, I find. These fundamental principles are now behind things like ChatGPT. Of course, technology is still a huge part to it. I mean, how to implement it in order to make it work, surely. And so, and then also using interacting particle approximations, very much at the core of the ensemble Kalman filter, also have come to the forefront. And that's something we want to exploit in future developments. And then, of course, the whole field of generative modeling, which I just alluded to, and the concepts, transformer architectures, which are behind large language models, and now up to revolutionizing potentially the field of numerical weather prediction, which is quite a story if you think about it. And it has a huge potential to also data assimilation and forecasting. Anyway, so now let me talk a little bit about one particular approach which I've been sort of working on the last couple of years in how to really bring together data assimilation and optimal control theory, and addressing this original problem that you really should take most of the uncertainties into account when you're trying to combine the two. And so this part is a bit more mathematical, so it's a bit more for the mathematicians in the room. But I will explain things, so hopefully it will be at least conceptual, but still remain clear what I'm trying to achieve. So again, some scary formulas, but not too, whoops, this is going very quick. So not too bad. So this is your controlled model. Let's fix the control for now, or drop the control. The next term is a term that is sort of machine learning-like, and it's there to characterize uncertainties. It's called the score, but it's representing uncertainties in the model in this case. The sign is a minus, not a plus. And then the last bit is actually the ensemble Kalman filter. Again, don't worry about the details. Here's the data. And you compare essentially data with what the model would predict. You take the difference, that's the innovation, and the innovation is then somehow projected onto the dynamics via covariances and so. But the key thing is you compare what the model is doing with the data, and then somehow you adjust. It's like that's the data-driven control term, right? So this is your ensemble Kalman filter. And I wrote it down in continuous time just to keep, I mean, like the data is assumed to come in continuously, but you can do it discretely. It just makes the whole thing a bit more messy. And then there's also, again, a model that describes the data in terms of the model variables and how they relate. And then there's, of course, an error again. I mean, a measurement error. OK? So, and then, you know, there are various terms in here. So the main thing is that, you know, you have to compute expectations of part of it, and that makes the whole thing more complicated. But it's addressable because you can now implement this as on a computer as an interacting particle system or an ensemble system. So basically, again, up here, that's the I is the ensemble member. So I goes from 1 maybe to 100. Typically, the ensemble size in metrology is 100 or something, a few hundreds maybe. So you run 100 copies of your forecasting system, and that gives you an uncertainty. It gives you a spread of what things can happen. We saw it in your slide as well, where you're showing that the things diverge. So in a chaotic system, they would all diverge mostly, and so uncertainty grows, chaotic systems. Then on top of it, you have model uncertainties, which will spread things even further, because you have random or perturbations that you have to account to for. And then this is counterbalanced by using data that pulls everything together again. So it's a constant fight between uncertainty increase and data reducing the uncertainty. And the terms that are needed is crucial is the covariance matrix, this covariance, which is characterizing the current uncertainty. It's like the second moment of your current, the spread. It's characterizing the spread of the ensemble, the covariance or the variance in your ensemble. And that's the crucial factor that tells you how much you should use the data and how much you should not use the data, because there's uncertainty in the data, there's uncertainty from your model, and you have to balance the two things in a Bayesian statistic sense, right? But this is now easy to approximate, or well, quotation mark easy. You can compute conditional. You have an ensemble, and you just estimate the second moment. As you learned in statistics 101, essentially. So this is all very implementable. And again, I can only refer to Miyoshi to tell you all the difficulties, of course, there are there. But it's now a routine procedure. It's worldwide used in Germany, in the UK, and So it's a tremendous success. It's really stunning. It's as stunning as well, I would almost say ChatGPT, but maybe ChatGPT is a bit more stunning. I don't know. Anyway, but it's a huge achievement, and it's sort of, there's a wonderful paper actually, the quiet revolution of numerical weather prediction, which sort of outlines the huge success numerical weather prediction is. And we often forget about this because we just take it for granted. But it's an amazing story. And again, it started with John von Neumann and Charney, and meteorologist. An interdisciplinary project, very much like this. It started as an interdisciplinary project where meteorologists came together, Charney leading and John von Neumann. They had a vision, and they pushed it through. Anyway, so now what can we do? I mean, this is, again, standard data assimilation. So now what are we going to do about control? So I already mentioned briefly model predictive control. Just to tell you the basic concept of model predictive control is that you look at a small window and say, I do a short-term prediction, and over that short window, then I do a control term, and I solve an optimal control problem, assuming I know where I am, and basically ignoring all uncertainties, right? So the current state is given, and the dynamics is also deterministic, so to speak. And then that little control optimization problem can be solved very efficiently. And then you do this all along. So you move along with a sliding window, receding horizon, and adjust the controls. And you compute the controls online. Now, chemical engineering has been extremely successful. There have been attempts to also include uncertainties, but chemical engineering is nothing like metrology. It's very robust. There's no chaos, right? So, yesterday I saw talks that try to develop this idea of model predictive control further, and I'm very curious to see how far we can push this, but it's certainly much more challenging in the context of metrology than it is for chemical process engineering. And the other thing is, the other big field in control, the other big game player, is the machine learning community in reinforcement learning, which is almost a complete orthogonal approach, where you say, I look for the stationary control laws which optimize the cost function, et cetera, and it's based on the Bellman principle and the Bellman equation, and you're basically approximating a value function. And it can be done model-free. Again, it's a huge success story. But you can already see it looks very, very complicated, right? This is it's a partial differential equation, essentially, you have to solve. Now, the good thing is you have to do this sort of once for each scenario, maybe. So you can do some stuff offline. It's not all online. And of course, if you manage to solve the problem, then you have the control given as a gradient of that function you get from this PDE. So yes, but I think in general reinforcement learning works in relatively low dimensions. Again, metrology is a completely different game, right? Very high dimensional. Even the effective dimension is high, right? So I have not seen anything reinforcement learned applied to this in that dimension. So both approaches have promise, but they also have severe limitations. So there's a third method. It's going back to Pontryagin. And it has been popular for a long time, and then it fell a bit out of favor. I don't know why. It also took me a long time to get back to it. But now I'm actually really excited about it. I mean, I think it's really cool. It's just an amazing, this is such an amazing idea, right? So basically, Pontryagin also looked at the deterministic case, right? So where you want to solve the control U under some cost. And then the key idea of Pontryagin was he introduced co-states. And the co-states are of the same dimension as the states, right? So, okay, so that doubles the dimension of the problem. That's a bit of a problem maybe in metrology, but okay, it's just a factor 2, right? And then you introducing a Hamiltonian, like classical mechanics. Some of you remember classical mechanics, Hamiltonian, Newtonian equations of motion. So basically that's what he did. So there is the original cost, right? That's the cost function, a control cost. And then basically P acts like a Lagrange multiplier to enforce the dynamics. So P is like momentum. in classical mechanics, except there's no kinetic energy really here, so it's a little bit different. But otherwise, it's a Hamiltonian. And then once you have the states and the co-states, the optimal control is given in this form. You just minimize the energy, the Hamiltonian, over U over the control term. In this case, it's a nice quadratic function. I mean, in this particular case, because you have a quadratic penalty on the energy cost for the control. And so the minimizer is of this form. So you're done, provided you have the co-states. Now, what are the co-states? So you write down your Hamilton equations of motion, right? Classical mechanics. You know, sorry, I'm switching in German. I'm still a bit jet lagged. So, x is like position. X, you know, there's a motion, and that's the gradient of the Hamiltonian with respect to p, with respect to kinetic energy, so to speak, right? Except the energy is different. H is different. And then the momentum equation is the second one, where you take the gradient of h with respect to x. And here I've written down the equation. So the first equation is just the control equation. I mean, the forward ODE equation with control. And the second one is an equation you solve backwards in time. It's a sensitivity. P, the co-states, tell you the sensitivity of how you have to change things if you want to achieve a certain goal in the future. And you solve this backward in time. But it's still an ODE. You double the dimension, but it's still an ODE. But there's always a catch. It's a boundary value problem. So if you want to solve this cost function with this terminal cost, you solve the first equation forward, and the second equation you have to solve backward with this boundary condition, which is the gradient of the terminal cost. So you have a boundary value problem you have to solve, but it's still an ODE system. I mean, it's still, yeah, but it's a boundary. You cannot just go forward. So in principle, that's all good and fine. But of course, there's no uncertainty here, right? Nothing of uncertainty, right? You assume exactly where you start from. There's no modeling error. There's nothing. So it contradicts what I said earlier, that you should include uncertainty. So, how are we going to do this? It's possible. You basically, you go back to your good old ensemble Kalman filter and realize, okay, you want to get some sort of interacting particle system out of this. I mean, this is a single particle, so right? You solve from one initial condition, and you get a single forward and backward path, so to speak. Now think of a whole ensemble, a cloud of those that basically then characterize the uncertainty in a proper way, and like the ensemble Kalman filter, they will start interacting in defining forward the control, forward doing the data assimilation, and backward also interacting to get the controls right, because the control has to be the same control is applied to all ensemble members, right? Because you actually don't know which of the ensemble members is the truth. So all ensemble members have the same control, which you then also apply to the physical system. That's key, right? So that's the challenge. And of course, we have to do this in continuous time. We have, as I said, we want to introduce model errors, uncertainties in initial conditions, and we want to do it for partially observed states. And so we want to combine data assimilation. So, okay, so here we go. So we use Pontryagin. And instead of having a single Hamiltonian, we have a field of Hamiltonians, a density of Hamiltonians. For each of these members in the cloud sort of has its own sort of Hamiltonian. And that's the A. The A is basically saying that's this particular path in the cloud of all possible paths. In fact, the A's are distributed according to the uncertainty in the current estimate of your state, right? So that's how this cloud comes, where that comes from, because you're not sure where you are currently exactly. But you have a good representation through the ensemble Kalman filter. So that has a good particle representation. So we introduce this density of Hamiltonians, like a field theory now. We're doing a little like Einstein's field. It's not general relativity, of course, but it's like, you know, classical mechanics going up all the way up to, I mean, it's no speed of light here, right? It's all slow. But a little bit like this, right? So you go to a field theory, or Maxwell field equation or something like this. So there's a spatial component now. And so you have now each of these cloud ensemble member paths in this space of all possible paths, obeys its own sort of Pontryagin principle as we had it on the previous slides. And then there are two additional terms, which are key. The first additional term is the green one that comes from uncertainty. That represents model uncertainty. And the red one is the one that makes everything interact. It includes actually a bit like some of the formulations of Einstein's field equations, general relativity. It's a gauge variable which you can freely choose. It's again like a Lagrange multiplier, but you can freely choose it as it turns out. That was an amazing surprise we found. And it enforces basically the fact that the co-states are linked to the value function. I mean, I don't know if you remember the previous slides. I don't want to flip around here with slides. But when we looked at reinforcement learning, I wrote down Bellman's equation. And there was an equation in V, the value function. And we're trying to now to basically approximate that value function through the momentum co-states, which are actually the gradients of, pointwise evaluation of the gradient of this value function. Now, it's a bit technical, but I hope you at least get the connection to reinforcement learning where you actually directly approximate the value function. So now we're approximating directly the gradient, which are sensitivities. You're basically doing a sensitivity analysis. I mean, those of you who were at the workshop yesterday, there was a lot of talk about sensitivities in the second half of the symposium. That's exactly what these co-states are doing. The sensitivities with respect to your goal. And then once you have this Hamiltonian, the rest is Pontryagin again, Hamiltonian mechanics, now is a field mechanics. So the optimal control is given by minimizing the Hamiltonian, now integrated over all possible trajectories or A's, labels. That gives you the optimal control. It has this form. And so that's, but of course you still have to solve the equations. So first of all, you take the gradient with respect to beta, so you get a constraint type thing. That's exactly what I said. There's a link between the co-states and the value function you're trying to approximate. Of course, this ultimately we will have particles here and we will have particles here, so you have to solve a regression problem to find the function psi. The function psi is sort of the key outcome of the whole thing. But it's defined in terms of things that you solve as an ODE system. Okay, so here are the equations, right? So, the thing is, so you get an equation in X, which is like your data assimilation formulation. That's your model, controlled, optimal controlled. And beta is, as I said, you can freely choose. It's your driving term you can add. And of course, we will choose it exactly that it matches the ensemble Kalman filter. But you can take anything else. I mean, if you have another data assimilation scheme, you can use it as well. So that's your, basically, if you fix the U, that's your classical data assimilation weather forecasting system. Now you're augmenting this by a second set, the co-states. And the trick is, and I don't have time to go into the details how we're going to manage to do this, but now we're solving this equation also forward in time. So it's no longer a boundary value problem, but we're relying on a relaxation to an equilibrium so that we can solve both equations forward in time. So now we can just propagate the whole thing forward in time. It's a little bit like an extreme form of model prediction control. But reformulate an equilibrium problem, which is sort of hidden here. That's why there's an epsilon here. So if you make that small, then basically you can see that will be small, and then this is the equilibrium you're trying to follow. Not exactly, but you're tracking that. And that equilibrium is then close enough to the solution of a stationary Bellman equation. And then, here's the control, and here's the function psi. You need to approximate this way. And then here, as I said, the beta, you can put in the uncertainties. The uncertainty that comes from the model and the uncertainties that come from the data, or the reduction of uncertainty that comes through the data assimilation process. Okay, again, particles to the rescue. So if you particularize everything, then the first set of equations have like, you have 100 copies of your model, and it's really just the ENCAF, right? Data assimilation system and forecasting system. And then you get a second set, equal number of, a second set of equations, which are the co-states, and I left the middle things out, but it's all there. And it's, as I said, again, it's sort of a sensitivity analysis. So the interesting thing is if you have, one thing you will also encounter with these things, it's actually multi-objective. So it's very hard, I guess also in your problem, to say we have a single objective. So there will be multiple objectives and they will compete with each other, and you have to probably decide in the end which you give the priority. So this can be included here. You would have different co-states for different objectives. And then that will lead to different controls, and then of course the human in the loop has to decide which of the controls you're gonna maybe apply, or if you use a combination or whatever. But multi-objective control theory is, I think, will be essential, right? It's very hard, as I said, I don't believe that it's a single objective you can just say, that's it, right? I mean, because, yeah, there will be competing interests. And so, yeah, and then the implementation details, let's not worry about it. But you see the optimal control is then very easily given in terms of the co-states once you implement this as a particle system. Okay. Wrapping up, just two examples. One example, the second example actually has been developed as part of the Moonshot project. And the first one is a classic. It's an inverted pendulum. So you have a pendulum that hangs down and you want to excite, you have a force, you can move, basically there's a hinge and you can move, and it's on the car and you can slide the car forward and backward, and you want to move it so that the pendulum gets stabilized upwards. It's sort of a classic, robotics example. It's how we walk. I mean, like that we don't fall over in a way. Of course, we have feet, so it's a little cheating. We're not on a hinge, right? That would be hard. But that's sort of what a robot has to do, and controlling a robot. And so these are the equations for the pendulum. It's a mathematical pendulum. There's a bit of friction, and here's a control. And there's a cosine theta in front of it because the theta is the angle. Angle 0 is down, pi would be up. And and the control only acts on the acceleration when you move the car that's accelerating the hinge, essentially. And we assume that we only observe the angle, right? You can't see the velocity of the pendulum, or you cannot measure it. So it's partially observed. And so the goal is to move it up. So we take a quadratic cost function, but it's obviously a nonlinear control problem. It's actually a highly nonlinear control problem. And so I implemented the method I described for 3 particles. I'm using 3 particles. So it's a 2-dimensional system, and I use 3 particles. That's pretty good. So it would be a bit scary if I would have had to use 100 particles. I mean, how that's going to scale up. I mean, it's still a question how you're going to scale it up. But from data assimilation, we have a lot of wisdom on how to scale these things up. It's another one of these amazing stories that and again, in machine learning, you always have to explore structure. And there is structure, but it needs to be explored. Of course, that's still low-dimensional, so we don't need to explore any further structure. And you see it goes nicely up, right? So actually very quickly, right? So it starts down here. The velocities go up because you have to do quite a bit initially, and then it stabilizes nicely up there. And the fluctuations are due to the measurement error, right? It's not like the controller is sort of getting crazy. It's just because you don't have an exact state estimate, right? In fact, just as I'm talking here, I should have also given you the bars of the uncertainty. I'm just giving you here the best estimator. But I should also indicate the uncertainties actually, right? What is the band of the truth you thinking it is, and then, but the most important point I want to show you is really stabilizing the system nicely, even though you only partially observe it, and you solve everything forward in time. It's completely online. And then the second example is the Lorentz 63. I mean, that was already, again, and you mentioned it briefly in your talk about chaotic dynamics as a classic example, Edward Lorentz. And it's a 3-dimensional system where, we have a lot of theory for. We know exactly what the chaotic nature is and the attractor. And so this example, as I said, was set up as a control problem within the Moonshot program. The idea is that you only control, in this particular case, I only control the first component, the x component, of the 3 variables x, y, and z. I only observe the first 2 components, not the third. So it's, again, partially observed. And what one wants to achieve is that the x solution doesn't cross over to negative values. You want to force it to be positive. It's like you want to prevent some, you're basically suppressing the chaotic nature of the motion. And so that's the cost function, which was being used in the Moonshot. And again, now I'm using 4 particles, so 1 particle more than the dimension, and that's at least that I get a covariance matrix which is not singular when I estimate the covariances. That's a 3 by 3 object, so you need at least four ensemble members to estimate the covariance and the uncertainty. And then I also imposed, which is nice with the Pontryagin principle, you can add constraints. You can say the control should only not exceed a certain value, and the state should not go below or above a certain value. You can also, well, basically the way it's described here, you can enforce these sort of things. And so you see the solutions now really stay above 0, essentially, right? So the thing is becoming actually oscillatory, so it's no longer chaotic. The controls are pretty strong, but they limit it to 100, so there's a bit of a cutoff. And then the dynamics is, again, a bit fuzzy, and the fuzziness comes from the fact that you, again, only partially observe the process. So the controls are, when you apply the control, there's this uncertainty in there. So it's a bit of a random control as well, because you don't know exactly where you are. But you nicely control the estimation errors, so the truth, the data, and is nicely under control. Now, if you enforce a stricter limit, which you might, because you don't want to have such a strong interference with the real process, then you're losing some of it. So then suddenly you have some transitions, right? But it's not too bad. But that's something then that's the human in the loop has to decide, right? Where are the benefits and the losses? Let me summarize and wrap up. So, so basically we reformulated, combined, or I did, the data assimilation stochastic optimal control as a variational or Hamiltonian principle, Eulerian Lagrangian perspective, which is beautiful from a mathematical, and as I said, I convert almost to a mathematician, but I always still an engineer at heart. I really want to see things work as well. And so it can be implemented as an interacting particle system, and I don't think it adds too much overhead to the codes and things you're already having for data assimilation. And it's using this framework of interacting ensemble prediction particle systems. Yeah, but of course there's still a lot to do. And so I'm excited to hear what will come the rest of the days. I was very excited about the workshop yesterday. There were lots of inspirational talks and lots of ideas I took away. So I hope I will be able to continue collaborating with the project. And here are some references, and thank you for your attention.
Thank you for your presentation, Professor Reich. So participants, we have now time to take questions from the online and the in person. So do you have any questions or comments? Please, okay.
So thank you very much for inspiring talks. I'm Toshio Kyosuka from Kyoto University, working with Professor Kotsuki project, and I enjoyed your talk very much as a control engineer, being involved in this project. So, but I have a question about your marking evolution equation for the state and co-state. So it's really nice if you can compute the co-state forward in time as well as state. But so in my understanding, so basically the time evolution of the distribution could be described by, let's say, Fokker-Planck equation. partial differential equation.
Right.
And then, so in principle, we can derive the Euler-Lagrange equation for the infinite dimensional space. So that would be the exact formulation in my understanding. So, but yeah, I'm a bit confused. So do you have any, how to say, I guess there is some approximation or simplification deriving that evolution equation, or is it exact in principle?
That would be too nice if it's exact. So the analytic formulation, you're completely right. I mean, like there's a Fokker-Planck equation. Then because you have the data, you actually go to the Kushner-Stratonovich equation, which is a random SPDE.
Yes,
so it's an SPDE forward, and you get a backward SPDE as well from the control. So you have this coupled SPDE system. Now, the idea we're using here is that you can, I mean, if you have an SDE, you have the Fokker-Planck equation, and then you can reinterpret the Fokker-Planck equation actually as a McKean ODE. You know, I mean, you're using the score of the noise. That's actually where the noise, I mean, where the score came from here. I guess I'll just use this. So, oh, that's already moved. Oh no, we're still there. Where do I have it? Here. No, it's not here. So, no, it's actually here. Yeah, down here. So this is actually representing the noise. But now I'm using the score instead of Brownian motion. But in terms of the Fokker-Planck equation, it's exactly the same thing, right? The individual trajectories are different, but the distributions, which the thing we are interested in, is the same. It's like what people use in generative modeling. I mean, they have the diffusion modeling and they have the mean flow ODE formulations. It's the same idea. But this involves the score function, which actually, if you think of it as a particle system, that makes all particles have to interact to give the proper representation of the uncertainty in this picture. And I'm now, and that's sort of relatively well established in machine learning now for the Fokker-Planck equation, and now I've basically translated this into the Pontryagin picture. Though there are still approximations in the sense that I didn't take care about the uncertainty in the future observation. So that part is still missing. But I think I have a way to do it, but it makes everything a bit more complicated. But there is basically, again, there is a McKean formulation of the Stratonovich equation. So SPDE, you can also write as a mean field ODE system. Okay. So that's the underlying mathematics.
Okay.
Right?
Okay. So probably you mean the score function, something like some, how to say, diffusion model.
Yeah.
To, how to say, adjust the distribution. Okay.
Yeah, but here it's used to represent the uncertainty. In diffusion modeling, of course, you're using it to represent the data distribution, right?
Yes,
so there it's more, the sign is different. So here it adds uncertainty, but it's the same object, it's a score function. Okay. But in the other case, it's the denoising part.
Yes.
The score function is doing the denoising in generative modeling. Here it's doing the noising.
Okay.
But it's the same thing.
Okay.
Mathematically, it's the same thing.
Yeah, okay, I will check your paper for detail. Thank you very much.
Right. Yeah.
Hi. Thanks for nice talk. So it's very beautiful to reformulate like a data assimilation or a control problem into the same like problem. But the one thing we should think about additionally is maybe time delay for weather control. So there are some delays from the observation to the a computer, and for computing the weather forecast, we still need some additional computation. And so it means we can't add interventions immediately, and maybe such the time delay incorporates an additional uncertainty or difficulty. And my question is it possible to include such impact of the time delay into the same formulation or not?
Yeah, no, I believe it's possible. It would have made the slides even more complicated, right? It's already pretty dense. But yes, I've been thinking about this because, I mean, there's also the thing that you maybe have a cost function that actually is over a window. You don't want to exceed certain values over a time window, not just point-wise, but over a window. So then basically you would need to run the system without the data forward in time. And then see what but the beauty about it is that you would then, yeah, thank you. You would then not take the actual observations here. If you want to be, you can just, you take any observations. I mean, like you generate artificially observations according to what your forecasting model is doing. And then, of course, eventually we'll get the real observation that will then pin it down again to that value. But in principle, of course, again, it increases the layer of computational complexity. So the question is, how much can we afford to still remain real time? But it's all there in principle, right? But the practicalities, yeah, I mean, that's something I cannot yet answer.
Yeah, okay. And one additional interest of mine is maybe you would like also like include the optimal experimental design to optimize the sensor placement, maybe for reducing the uncertainty of control or weather forecast. Maybe this framework can also include maybe optimal sensor placement because the research field is very similar. And yeah, I would be, I'm pretty interested in your further like development.
Right, yeah, no, again, that's something I've been thinking about. Yeah, there's the experimental side. Experimental design is very closely related to this. Yeah. But I cannot yet give a concrete answer. But yes, there's clearly this connection. I mean, you know, even existing algorithms are very close to data assimilation. We're using, you know, data assimilation algorithms to also do placement, right? Sensor placement. So yeah.
Thank you very much.
Yeah, for the future. Next time. I don't know when.
You know. I'm looking forward to seeing.
Yeah.
Other questions? Comments? No? Okay. Okay. If not, so let us thank the speakers again. Thank you very much.
Thank you.